Hello! We looked at the matching game last time. We will look at a similar game this time, which is the network bargaining game. We start with a small example of the two-player bargaining game. Alice and Bob are negotiating over how to split $1 million. They can only take the money if both agree on how to split it. With all else being equal, the natural outcome is that both will agree to take $500,000 each. But let's complicate things a little bit. Suppose there are outside options. Carol offers alpha to Alice if they work together, and Dan offers beta to Bob if they work together. So what would make Alice and Bob abandon their negotiations and go with their outside options instead? And if they stick together, how would this change the negotiation over the $1 million? We look at two situations. First, suppose that Carol is offering $0.4 million and Dan is offering $0.7 million. Bob will work with Dan unless he gets more than $0.7 million from Alice. But then Alice will be getting less than $0.3 million, so she might as well work with Carol. So negotiation between Alice and Bob breaks down. More generally, this happens if alpha plus beta is greater than 1 million. Now let's look at a second situation. Suppose Carol offers $0.4 million and Dan offers $0.2 million. The combined offers is less than $1 million, so we expect Alice and Bob to still work with each other. But can you guess how Alice and Bob would split the money now? Well, Alice wants at least $0.4 million out of the $1 million in order to work with Bob. And Bob wants at least $0.2 million out of the $1 million in order to work with Alice. After that, there are $0.4 million left. We will just split them equally. So Alice gets $0.6 million in total, and Bob gets $0.4 million. So the outside options do affect the negotiations. The stronger the outside option, the more that a player gets. And this is called Nash's bargaining solution. Players A and B try to split W, and each has outside options alpha and beta respectively. If alpha plus beta is more than W, then no split is possible. Otherwise, player A gets XA, which is alpha plus W minus alpha minus beta over 2, and player B gets XB, which is beta plus W minus alpha minus beta over 2. We are now going to look at the network extension of the bargaining game. This game is played on a graph G, and the players are the vertices N equals V of G. Each edge E has weight WE, which is non-negative. An edge joins two players who are allowed to negotiate over the weight of that edge, and each player is only allowed to work with one other player in the end. So we are looking at matchings. The questions are, which pairs would negotiate successfully, and how do they split their value? Take a look at this example with a graph with 5 players negotiating. Every edge has weight 1. Generally, we will be looking at who has more negotiating power, which player is likely to get the most value in the situation. In this graph, one possible result would have these two matching edges and these payoffs. In this case, player B has the most powerful position. An outcome of the network bargaining game consists of a matching M and a payoff vector X, such that XU plus XV is equal to WUV for all UV in M, and xv is 0 if v is not matched by m, and x has to be non-negative. We are looking for a stable outcome. The stability of an outcome depends on the outside options of the players. But what does that mean in the network bargaining context? Say you have a player V, and V is adjacent to 3 other players A, B, and C. V is currently matched with C. But V could negotiate with A and B as well, and see if they can get a better deal. Now suppose that A is currently getting a payoff of 0.7, and B is currently getting a payoff of 0.2. If A is to work with V instead, then A could offer 0.3 to V. That is, the value of the edge AV, which is 1, minus the current payoff for player A, which is 0.7. Similarly, V can get 0.8 by working with B. And this is the best option possible outside of V's current matching. And this leads to our definition of the outside option. For an outcome mx and a player u, the outside option of u is alpha of u, which is the maximum of 0, and wuv minus xv for all the edges uv that are incident with u but is not in the matching M. This is the maximum value that U can get by defecting from their current partner in the matching M. And there is no need to defect if alpha of U is less than or equal to x of U. Meaning, the best option you can get from switching is no better than what you are currently getting. So an outcome mx is stable if alpha of u is at most x of u for all u in N. Take a look at this example here and try to calculate the outside option for each vertex. We see that A has no other players to negotiate with, so alpha of A is 0. For B, they have 2 players to negotiate with. Player C could offer up to 1, that is 1 minus 0. And player D could offer up to 1/2, that is 1 minus 1/2. So alpha of B is the maximum of these 2 numbers, which is 1. And all remaining alphas are zeros. And you can check that this is a stable outcome. All the alpha values are less than or equal to the x values. Now, to be stable, for each edge uv, xu has to be at least alpha of u. But alpha of u is also at least wuv minus xv. That's from the definition of alpha. So xu plus xv is at least wuv. This might look familiar to you because this is in the script C prime from the matching game. So as long as x is in script C prime, then we have a stable outcome. So here is our proposition. A stable outcome exists in a network bargaining game if and only if the corresponding matching game has a non-empty core. Here is another example of the network bargaining game. It is a tree, so it is a bipartite graph. Using our result from before, this must have a stable outcome. We need to find x in the core of the matching game. We need the maximum matching, which is this. And we can use the LP to solve for x, or just try values. And here is a set of numbers that I came up with. We just need xu plus xv is at least wuv for all edges uv. And you can check that this is a stable outcome. Now, stable outcomes are good, but in reality, when experiments were done with real people negotiating, they are not always the one that is agreed on. We will see a more refined version of stable outcomes in the next lecture.